Welcome everyone to our monthly Zoom webinar called Nodutalk, an initiative by Castrol Foundries. Today is the third episode. We are going to cover in this episode a matrix control in SG iron through chemical composition.
Namaskar. Good afternoon, friends. Before I go to the main topic, I have a nice question which I would like to answer before I move into the main topic. The question was asked to me while making grade 500 by 7, we get higher tensile strength but lower elongation. Customer also demands a minimum BHN of 180 on casting or section thickness 15 to 30 millimeters. You got the question? While making grades 500 by 7, they get higher tensile strength but lower elongation. Customer also wants a minimum hardness of 180 on casting section thickness 15 to 30 millimeters. Now, it is clear. We have seen the role of composition in the first two uh, episodes. The base metal should be around carbon 3.8%, silicon 1.2 to 1.4%. This is base metal before the magnesium treatment. Then final casting composition, carbon around 3.7%, silicon 2.3 to 2.4%. Manganese, I would like to have always manganese zero point 0.3 max. You can have a little bit more, but manganese 0.3 max. Copper 0.25 to 0.35%, sulfur 0.02 max, and phos 0.03 to zero point zero 0.04 max. Keep the inoculation level of 0.3 to 0.5% silicon using any good grade of ferrosilicon inoculant. The nodularity should be more than 85%. Matrix should consist of approximately 30 to 45% pearlite and the balance ferrite. Try to keep silicon at 2.4% max. At the same time, no carbide should be obtained in the matrix. Hardness can be increased by addition of about 0.3% copper, which will give about 30 to 40% pearlitic matrix. Now that we have answered this question, we'll start with the main topic of today. The structure of ductile iron consists of spherical graphite particles embedded in a ferrous matrix. Graphite occupies around 8 to 10% by volume of the structure. That means the iron matrix constitutes about the remaining 90%. Therefore, the matrix structure determines properties of SG iron. As soon as ductile iron solidifies around 1150 to 1130 degrees centigrade, its structure consists of austenite with about 1.7% carbon dissolved in it. As the iron cools, carbon becomes less soluble in austenite. So it migrates by diffusion to the graphite nodules, making them grow. If the cooling if the cooling is slow, the austenite transforms into ferrite at about 723 degrees Celsius, resulting in a structure of graphite nodules in a ferritic matrix. This is the structure below. If the cooling is faster, austenite turns into pearlite or a mixture of ferrite and pearlite, as there isn't enough time for carbon to diffuse with graphite. If you look at the structure of pearlite below, it is a structure consisting of ferrite and iron carbide or cementite. That's the structure of pearlite, ferrite, and alternate layers of ferrite and iron carbide. The great majority of ductile iron castings are essentially unalloyed, with matrix structures of 100% ferrite or 100% pearlite or mixed proportion of the two. Ferrite is soft and ductile, while pearlite, which I told you is a mixture of cemented and ferrite, is harder and stronger. The properties of ductile iron are significantly influenced by the matrix structure around the graphite nodules, not the nodules themselves. Because you have seen matrix structure is around 90% and the graphite structure is only about 8 to 10%. So what are the various ways to get the different matrix structures? One is the chemical composition. Minor compositional differences between different grades of ductile iron are used to create the desired matrix. Next, the cooling rate. The rate at which the molten iron cools during casting affects the formation of the matrix phases. Next, heat treatment. Heat treatment processes like annealing, hot tempering, and quenching can alter the matrix structure and properties. And finally, the nodule count. Number of nodules also decides the matrix structure. These are the common matrix structures which we are familiar with: ferritic, is a pure, ductile, and flexible iron with low strength. Pearlitic is a mechanical mixture of ferrite and iron carbide, pearlite I told you, offering higher strength and wear resistance. Pearlitic, a mixture of pearlite and ferrite, the most common matrix for commercial grades of ductile iron. Phosphorite, Phosphoritic, the matrix consisting of ferrite and phosphorite phases, achieved through tempering heat treatment process. This is the structure of ferritic, ferritic matrix, and the pearlitic matrix. You can see the bullseye structure in the pearlitic matrix. The other matrix structures which are seen in ductile iron are austenitic and austempered. Now let us see the effect of matrix structure and mechanical properties. Ferritic matrix has high impact resistance and good machinability, but very poor wear resistance. It's a softer, very soft material. So it has high impact resistance, good machinability, but poor wear resistance. Pearlite matrix has got high strength, good wear resistance, moderate impact resistance, and good machinability. Pearlite ferrite mixed matrix is a balance of strength, ductility, and machinability. Ferritic structure or the austemper structure consists of high strength, high toughness, and high wear resistance. The austempering heat treatment process, it transforms the austenite into magnetic ferrite, resulting in a matrix with high strength and toughness. Allowing elements like molybdenum, nickel, copper, and tin can be added to the alloy to influence the formation of different matrix structures. You can see the matrix structures below from left to right: ferritic grade, ferritic grade, pearlitic grade, martensitic grade with retained austenite, tempered martensite, ADI high toughness, ADI high wear resistance, and austenitic. The number of graphite nodules in ductile iron affects the amount of ferrite and pearlite in the matrix. Listen to this very carefully. The number of graphite nodules in ductile iron affects the amount of ferrite and pearlite in the matrix. Higher nodule count gives you more ferrite. Generally, more ferrite nodules leads to a ferritic structure, making the iron softer and more ductile. Each graphite nodule acts as a carbon sink, where excess carbon moves during cooling. If there are more nodules, carbon has a shorter distance to travel, leading to more complete transformation into ferrite. Hence, if you want to make a ferritic structure, you must increase your nodule count. We speak about the Pearlite promoters. The balance between ferrite and pearlite determines how the material will respond to different types of stress. Combination of ferrite and pearlite are tailored to the application. Adding elements like copper or tin can also influence hardness by promoting pearlite formation. The figure on the side shows the percentage ferrite increased by adding copper, increased by adding tin, and the effect on the hardness. So this is how the balance between ferrite and pearlite determines how the material will respond to different types of stress. Let's look at the key points to be considered. Manganese is not preferred for pearlite promotion. We have discussed this thing in details last time. That's why we have given a cap to manganese. Manganese should not be more than 0.3%. Avoid phosphorus, titanium, manganese, and chromium for this purpose. Molybdenum and nickel are effective but costly. Moly also promotes cell boundary carbides. Copper and tin, therefore, are the most efficient alloying elements for pearlite promotion in HDI. The table on the right indicates the relative pearlitic forming effectiveness. Tin is the most powerful pearlite stabilizer, and nickel and copper, chromium are less effective. The cooling rate and chemical composition influences matrix formation. Matrix structure controls mechanical properties. Same composition gives different matrix structure. We have seen. So, a typical relationship between elongation and yield strength of ductile iron with different matrix structures. The highest yield strength is achievable with fast-tempered ductile iron. Then we have magnetic ductile iron. Then we have ferritic, and austenitic. Now we look at the role of alloying in ductile iron. controlled heat treatment and alloying gives wide range of matrix structures. Alloying helps in achieving customizable mechanical properties. Alloying helps to promote pearlite. It enhances high temperature properties. It helps to achieve benetic or ADI structures and with other alloying benefits. Let's look at the role of the various elements. Carbon has no direct effect on matrix structure, but it controls the formation of ferrite and pearlite. In silicon, silicon influences pearlite-ferrite ratio, affects hardness, impact resistance, ductility, and thermal conductivity. As the silicon content increases, look at the graph, as the silicon content increases, the Brinell hardness increases in both annealed ferritic iron and as cast ferritic iron. Phosphorus should be avoided. It promotes pearlite but reduces ductility, toughness, and weldability of ductile iron. Hence, should be minimized and kept to less than 0.03%. I know it is difficult, but this is what is required if you want to improve the pearlite formation and avoid the reduction in ductility, toughness, and weldability. Manganese controls carbide formation. It influences pearlite levels indirectly. Copper, as a pearlite enhancer, is a very good element. It helps to form pearlite without creating carbides. It encourages graphite formation, so it's considered a safe and effective choice for promoting pearlite. It does not deform graphite. So there are certain limits. It can dissolve up to 2.5% in ductile iron, but it should be kept below 1.5% to maintain proper graphite nodularity. Let us compare copper as a pearlite enhancer. Comparing copper and manganese, copper is 5 to 10 times more effective than manganese as a pearlite enhancer. The study found that 0.82% copper could create a fully pearlitic matrix, while 1.74 manganese was needed for the same result. Manganese also formed undesirable carbides. The impact of this element on properties. Copper reduces impact strength and increases hardness by refining the pearlitic structure. It also raises the brittle transition temperature, meaning the material becomes brittle at higher temperatures. What are the purity concerns? Only pure high purity copper should be used. Impure scrap may contain harmful elements like arsenic, lead, tellurium. When copper should be avoided, for fully ferritic structure, copper should be kept below 0.03% as it promotes pearlite. Copper is an excellent pearlite former, but selection should be carefully controlled based on a required matrix structure. These are some effects of copper in the top slide left, 1.6% copper, on the right, 1.74% manganese, again at the bottom left, 0.82% copper, and on the bottom right, 1.33% manganese. This is on the top left with 0.2% copper and 1.14% manganese, almost the same structure. And at the bottom, unalloyed, the same as before adding manganese and copper. Manganese was present about 0.25% in the ductile iron. Tin increases hardness and strength by promoting pearlite. Tin increases hardness and strength by promoting pearlite. Tin is a strong pearlite promoter that does not form carbides, even at levels up to 0.15%. How does it work? It works by forming a barrier around graphite nodules, preventing carbon diffusion and leading to a pearlite formation. Tin is 10 times more effective than copper in promoting pearlite. Upper limit 0.03 to 0.08 tin, depending on section thickness, is enough for a fully pearlitic matrix. Tin as a pearlite enhancer. Strict limit maximum 0.1% tin to prevent brittleness and cracking. At high levels, tin accumulates at all cell boundaries, forming a brittle film that weakens the castings. Purity concerns. Tin does not burn off during remelting of the returns, so its content must be carefully managed. Scrap containing tin must be separated and accounted for in the production. When to avoid tin? The maximum allowable tin for ferritic ductile iron is 0.01% to prevent unintended pearlite formation in ferritic iron. Tin and copper combination as pearlite addition. Tin and copper together have an additive effect on pearlite formation. This combination helps eliminate bullseye structure, achieving maximum hardness. Recommended limits for these elements 1.5% copper and 0.08% tin to avoid defects. Molybdenum as a polymer enhancer. Molybdenum increases hardness and yield strength through solid solution strengthening in ferritic ductile ions. At high temperatures, molybdenum significantly boosts strength and ductility. Usage limits and up to 1% molybdenum helps achieve pearlite-free martensitic structure in either as cast or heat-treated condition. Up to 2% molybdenum improves tensile strength, stress to rupture, creep strength, and thermal fatigue resistance. Carbide formation risk increases when molybdenum exceeds 0.3%, especially in thick sections. If molybdenum added thick sections, it should not exceed 0.3% to avoid risk of carbide formation. Molybdenum's impact on properties. Each 1% molybdenum addition results in 42% increase, 42 megapascal increase in tensile strength, 15 points of hardness increase, and ductility reduced by 8%. Elongation reduces by about 8%. Purity concerns. Molybdenum tends to segregate in slow cooling thick sections, forming grain boundaries. This segregation effect worsens when combined with elements like chromium, manganese, or vanadium. When to avoid molybdenum? Molybdenum should be controlled in thick section castings to prevent excessive carbide formation, which reduces machinability and ductility. Overuse of molybdenum can lead to brittle structures, making castings prone to fracture under stress. Thick sections, molybdenum should be controlled. Overuse of molybdenum can lead to brittle structures. Controlling nickel. Nickel is a very, very nice pearlite stabilizer. By controlling nickel content, it is possible to optimize ductility, machinability, and high temperature performance without compromising the material's structural integrity. Nickel is soluble in iron at all concentrations, making it effective in modifying microstructures without forming harmful compounds. Improves low temperature properties in ferritic ductile iron. Improves tensile and proof strength in low silicon ductile iron. Reduces carbide formation. Nickel lowers the tendency for chill and carbide formation, making it beneficial for as cast ductile iron. Nickel as a product enhancer. Usage limits. Typically, 0.5 to 4% nickel is added to improve the hardenability of ductile iron. 18 to 36% nickel is added to achieve austenitic matrix used in ductile nail resist alloys. However, nickel reduces carbon solubility in iron, lowering the eutectic carbon content by 0.06% for every 1% nickel addition. When should nickel be avoided? Avoid nickel when you are making ferritic ductile iron. Can you go to the previous slide, please? Just for a minute. Previous slide. Yeah. Avoid nickel. Avoid excess use of nickel in ferritic ductile iron. Yeah. What is the effect of nickel on the impact on properties? With 18 to 36% nickel, a fully austenitic ductile structure forms, leading to ductile resist alloys that resist deformation at high temperature. Improves high temperature strength, enhances the material's ability to withstand thermal fatigue and creep. ADI may be allowed with nickel 1 to 2% and moly 0.3% maximum in section thicknesses above 12 millimeter sections to have control over these sections. Heat treatment and achieve required ferritic matrix. This table summarizes the effect of the elements which we discussed on the maximum recommended ranges, on their effect on stable and metastable eutectic, effect on matrix structure, effect on hardenability, effect on graphite structure, and segregation direction. This is a summary of the effect of matrix structures on the properties. On the left hand side, we have the matrix structures ferritic, pearlitic, ferritic, pearlitic, venitic, martensitic, and austenitic. And on the top, we have matrix properties like strength, toughness, ductility, hardness, and wear resistance. So you can get an idea about the effect of the matrix structure on the mechanical properties. So most ductile ions have a ferritic or pearlitic matrix, where different structures can be achieved by controlling the cooling rate and adding alloying elements. Other matrix structures are austenitic, martensitic, venitic, and ADI or austempered ductile ion. These are the references used in the presentation. Thank you.
MTech Castech Rajkot Dr. Saab is asking, what may be the reason of the lower hardness in perlitic grades? Tensile strength and microstructures are okay as per the specification.
Well, this is a tendency seen recently in most foundries.
Yes.
They make the quality grade castings with everything okay, but the hardness is low. And earlier, I was suspecting in one of my visits where similar problem occurred that the boron may be the culprit. Boron may be on the higher side in the charged materials, which has resulted in polytic structures not getting the required hardness. I don't have the number just now, but boron should not exceed ppm level in the iron because more than that 6 ppm level of boron causes hardness drop in polytic grades of ductile iron. Boron does not have any effect on the ferritic grades of ductile iron. It does not affect the hardness, but boron in polytic grades of ductile iron causes hardness drop. I would suggest that this gentleman check the analysis of the casting with polytic grade and lower hardness to see if boron is present and if it is present in the levels more than 6 ppm. 6 ppm means 0.0006%.
On page number 11, we have mentioned the table, what is the permissible limit, and 12th nodule tape is on that only. Area is chemical composition not getting the desired hardness in perlitic SG iron. What could be the reason? So the check boron level, it should be as low as 0.0006%. Also affects the hardness. This is the most likely cause of not getting a hardness in a perlitic SG iron. Friends, but your most of the foundries, the spectrometer is not calibrated to measure such a low level of
Yeah.
boron. So
No,
ideal thing is,
no, you said most of the structure. With the first two episodes and today's episode, you will realize that a lot of elements can get into the raw materials and affect the microstructure and the matrix structure and the properties of ductile iron. We just had an example of possible influence of one of the elements on the lower hardness and quality grades. Unfortunately, most of the foundries making ductile iron do not have a range of channels in their spectrometer to detect and get the concentration. If they have the channels, they may not be having the calibration standards, CRM standards for calibrating those channels. So you require at least for every element 2 or 3 CRM standards to fix the line in the spectrometer, which converts the intensity of light into the concentration level of that element. Therefore, most spectrometers do not have the channels, or if they have the channels, they may not be having the calibration standards to calibrate the spectrometer channels. Is that clear?
so sir, what is the option? They have to change the scrap source once and take one heat and check whether it is coming out okay or what?
Well, that's why the raw materials are control is very important. We will talk about the raw material controls in one of the next episodes. You have to keep your raw materials and process control intact to produce any grade of SGI. I mean, it is easier said than done.
Sir, we have already changed raw material as you are telling, but the result was same.
Well, mostly the factor which I indicated, boron, is, is responsible, but if the results are same, have you checked this, after changing the material, the amount, the level of boron in the matrix of material of the casting?
Sir, our spectrometer is not capable to analyze boron.
Yes, I know that was a previous question when Amish asked somebody. You may have to get the boron analyzed from outside lab that has got the facility for checking the coin sample of the material where it is suspected boron content. No, if
So
you
there
don't
is
have the boron, of course, you cannot check it. You may have to get it checked from an outside laboratory that has a facility to check boron with a calibrated boron channel on their spectrometer.
okay, sir.
Thank you.
So there is a second question by Mr. Vinayak Chikhode. For 500 by 7 grade, required a 200 plus BHN without compromising the strength and elongation. Kindly share the charge mix and composition.
Charge mix, I will have to discuss after we discuss the requirements of charge mix next time. But I had this similar question was asked in the beginning, and I've answered that thing. The suggested chemical composition is the base metal should be around 3.8 carbon, 1.2 to 1.4 silicon. The final casting should have around 3.7% carbon, 2.3 to 2.4% silicon, zero point 0.3 maximum manganese, copper 0.25 to 0.35. You can increase the copper to 0.4 if you want. Sulfur 0.02 max and phosphorus 0.03 max. Keep the inoculation level of 0.3 to 0.5% silicon using any good grade of ferrosilicon inoculant. Nodutality more than 85% minimum. Matrix should consist of 30 to 45% perlite and balanced ferrite. Try to keep the silicon level to 2.4% maximum. At the same time, no carbide should be obtained in the matrix. Hardness can be increased by adding of around 0.3% copper, which will give you about 30 to 40% Pearlitic matrix.
Next question is Mr. Bhagwan Barat. What is the reason of high tensile strength in 550 by 600 grade? We are getting elongation about 8 to 10%, but the tensile strength we are getting is 700 MPa and above.
Yeah, that only means you got too much of pearlite in your structure, isn't it? You should, if you want to lower the tensile strength, the amount of a little bit of ferrite should be present. The tensile strength will come down. The elongation is already more than required, 3% in a pearlite structure, right? You require 3% elongation, and you're getting 8%. So if you want to reduce the tensile strength,
6% required.
sorry,
Required is 6%, sir.
elongation,
Yes.
and you are getting how much?
We are getting around 8.
It's okay.
Yeah,
You
but
require
tensile we are
6% minimum. You are getting 8. That's okay.
yeah, okay, but we are tensile getting around 700. So why it is getting high?
The tensile is getting high because your pearlite is too refined. It's ttoo dense. Are you adding
Okay.
copper or you are adding tin?
No, we are adding only copper.
How much is the copper level?
Is a 0.3.
Oh, with 0.3, I know section thickness.
Section thickness is around 75 to 80 mm.
Oh, 75 to 80. And there you are getting very dense pearlite and very high tensile strength.
Yes.
I'm surprised with 0.3 copper, you're getting such a high tensile strength, almost very, very dense pearlite.
Yes, sir.
Should you be reduced? Should you try to reduce the copper? Is there any tin present?
No, sir, we
Knowingly
are
or
not adding
unknowingly?
a tin.
No, you may not be adding tin, but do you suspect that tin may also be present along with copper?
So that we have checked in our spectrum.
Hmm.
So SN is not present, just only there is a allowing adding by only copper, and that we are getting. First, we have taken trial with the 0.5 copper.
No,
Okay, so that
increasing copper will not reduce the tensile strength. Increasing the copper will only increase the amount of perlite and therefore increase the tensile strength. And section thickness is 75 millimeters to 80 millimeters, almost 3 inches. What is the level of manganese in your casting in this heavy
sorry, sir.
section? What is the
So
Excuse me. What is the level of manganese in this heavy section casting?
manganese is around 0.25 to 0.3.
Yeah. Manganese level is just perfect. No, there must be something else in the composition which is causing such a dense pearlite formation in heavy section casting.
And Bhagwan bhai, one more thing I would like to ask. By getting 700 MPa tensile, what is the problem which you are facing?
Okay.
Problem, right? Problem, there is no nothing, but just customer requirement is a 550. Tensile is high. There is any scope in chemistry. So that's why I'm asking you question.
Okay, got it.
No, 550 is the 550
Minimum.
is 55,000. So what does that correspond to? It probably corresponds to 700 megapascals.
550 is
Uh,
megapascals.
550 megapascal?
Yes.
No, how can
550
that
by
be?
6%.
So that is Pearlitic ferritic matrix.
Pearlitic.
No, 550 is Pearlitic matrix. No? What is the hardest required? What is the hardest required?
Hardness is 190 to 245.
So that is Pearlitic matrix, my friend, not Pearlitic.
Sir, Pearlitic for ferritic.
Yeah. If you
Okay,
look,
Bhagwan bhai, what I suggest, if you can share the microstructure and the char chemistry, we will,
Yes, yes.
yeah,
and
we will.
also look at the customer specification for this mechanical properties. What does the specification specify for the microstructure and for the mechanical properties for this grade?
Okay.
Okay.
Okay. Okay. Yeah.
So
Thank you.
Thank you.
next,
Thank you, sir.
next question is from Mr. Ravindra Kolor. What are the most of the benefits of adding high density alloys? So, Mr. Kolor, this question is not very clear. Can you unmute yourself and ask what you would like to ask?
High density alloys means we are adding copper magnesium in 500 grade. So
Okay.
is there any extra
Copper
benefit or
magnesium.
limitations? Yes, copper magnesium, that is high density alloy.
Oh, just like ferrosilicon magnesium nickel alloy, and you have got nickel
Yeah,
magnesium alloy,
yeah.
you have got copper magnesium alloy.
Yes,
So,
sir. Because our casting sizes are heavy. To avoid the fading effect, we are adding. Just that is also just 0.1 to 1.15%. Hello.
I have to, Amish, I've understood his question. I have to think about it. I'll get back to you.
Okay. Okay. Mr.
He's
Ravindra
adding,
Kolor.
copper magnesium alloy to get the SGIN
Yes.
Yes,
as
sir.
against ferrosilicon magnesium alloy.
Again, along with
So
ferrosilicon magnesium alloy.
you're adding both of them.
Sir, 1.1% to ferrosilicon magnesium alloy we are adding, and 0.1% copper magnesium we are adding to avoid the fading effect.
Uh, this I have not understood the question. I mean, I'm trying to understand. You're adding 1.2% ferrosilicon magnesium alloy and 0.1% copper magnesium alloy to avoid magnesium fading effect in your castings.
Yes, sir.
Have I understood your question?
Yes, sir.
Let me think about it. Okay.
Okay, no issue, sir.
Okay, thank you.
Okay.
Sir, can I add on something on this?
Sure.
Yeah,
Yes.
many of our customers are using copper magne combination of copper magnesium plus ferrosilicon magnesium as well as nickel magnesium plus ferrosilicon magnesium. The basic idea is using copper magnesium, Mr. Color, is it is a high density alloy, so it doesn't float on the surface of the liquid metal just like ferrosilicon magnesium, which is having a lower density. So you will
Yes.
get better recovery of magnesium and your addition
Right.
rate can be reduced. Okay.
And
Now,
we are getting benefit of copper also by adding
yes.
this one.
Yes, yes. But that is what I have calculated. Most of the people use these route when they have a restriction of silicon addition in the castings, because copper magnesium or nickel magnesium doesn't contain any silicon, and they have some limitation on a final silicon content. So they use pure copper magnesium, pure nickel magnesium, or combination with ferrosilicon magnesium.
Yeah,
Uh,
right.
but but as you said, you are adding 1.1% of ferrosilicon magnesium and only 0.1% of copper magnesium. So
Yes, sir.
which translates to about, because copper magnesium normally has 80 to 85 percentage of copper and
Correct.
balance is magnesium between 15 to 20% of magnesium. So by
Right.
0.1% magnesium, 0.1% copper magnesium, you are adding 0.08% of copper only.
Correct.
I don't think it is actually adding any advantage to your process or fading resistance, which you are
Yes.
looking at. But if it is working okay at your end, you can continue the practice. Otherwise, you can increase the copper magnesium percentage, of course, if cost allows, because addition of any alloy then pure metal is costlier. Of course, it has a own advantage, but you can derive the benefit by increasing the quantity of copper magnesium and reducing the ferrosilicon magnesium alloy.
Correct. But the problem is actually in the base metal, we are maintaining copper minimum level. After
Okay.
adding the copper magnesium, we are getting as per our requirement. So that is the benefit.
Okay. What is your treatment ladle size, sir?
Size actually 6 tons, sir. And
So,
for 700 grade, we are adding nickel magnesium
okay.
because our casting sizes are very big. The time is also very higher side only, pouring time. So to
Okay.
avoid the fading effect, we are adding this one.
Yeah. So that
Okay,
is
sir.
okay, but you can consider, and we will wait for Dr. Basutkar's reply also in due course. He will study the matter and he will come back to you.
Okay, thank you, sir. Thank you.
Thank you, sir. The next question is from Mr. Arif Vora. He's asking, we had a problem with the same methoding of 60 raised to 40 raised to 10 SG iron grade castings are okay. And in SSS 450 by 18 grade, we face the riser neck shrinkage and also the macro draws, also the more draws in the castings.
There are two questions. They are having a shrinkage at the riser neck in the casting.
In one
And
particular grade which is 450 by 18 solid solution strength and grade.
and the next problem we are facing is DOS problem in the casting, right?
Yes.
Okay. First, by changing the methoding, he said. So you were asking the question regarding methoding, the effect of methoding on this the defects.
Mr. Arif, can
Are
you
you
unmute yourself and
Hello.
explain? And
Yeah.
you can also mention the weight of the castings.
Good evening, sir.
good evening?
Sir, our casting is 6 ton weighing, 6.2 tons weighing cylinder casting,
Mm-hmm.
and we are making the casting since in 60-40-10 grade, but there is no issue in riser neck shrinkage. But when we have taken a trial for SSS grade, we are having this neck shrinkage problem. Sir, what may be the cause? Carbon is around 3 to 3.1%, and silicon is 3.3%.
Silicon is
3.3%.
yes. That's a SSS grade, right?
Hmm.
What is your pouring temperature for the 6 ton casting?
Pouring temperature is 1350 to 1360.
And the casting section thickness?
Section thickness at the junction of the riser neck is 120 mm.
So the riser is
Riser is 9-inch insulating sleeve, 16-inch height, and neck size is around 134 mm thickness.
yeah. It's a heavy section casting, and the riser neck
And
is
riser is cold riser, sir, not hot riser.
oh, it's a cold riser. Okay. It's not a hot riser. Fine.
Yes.
So the riser is helping the heavy section over there, but the riser is not able to um, provide sufficient metal to the section. Therefore, there is shrinkage in the riser neck. So you will have to either increase the riser diameter or the height of the sleeve, or increase up the sleeve height.
Actually, sir, calculated riser sleeve was coming around 8 inches, but for safer side, we have taken 9 inches.
You have taken the safer, but you are not getting the safe casting. No? So probably
So
you need to go to the next level.
in 60 40
Probably
10,
if there's a
there is no
sorry.
neck shrinkage. Only changing the grade gives us
Yeah,
neck
well,
shrinkage.
see, this is a high silicon high. The carbon equivalent is almost close to 4.2%, isn't it?
4.2 to 4.28%. We
Yeah,
are maintaining that.
4.2% of carbon equivalent. So I think you may have to try increasing the feed metal from the cold riser.
I could not
This
go ahead
sleeve is
with
an
that.
insulating sleeve or is it an exothermic sleeve?
Insulating sleeves.
The metal is okay, but there is not sufficient metal from the riser because the section needs more metal. And it's not able to get the required metal from the riser, and therefore there is shrinkage at the neck.
Sir, we have cut the riser from center line also.
Hmm?
There is no piping shown in the riser. Only in center line there is that segregation type of shrinkage in center line. in
No,
high rise.
please repeat the thing after. Please repeat after sectioning the riser.
I have sectioned the riser, and
Yes.
there is only in center there is some you can say segregation type porosity, means spongy surface, means structure.
Yeah.
There is
That means
no
that
any piping in the riser.
that's okay. The riser is doing the job because if there's more metal when the heavy section is getting solidified, it is releasing graphite, and so the metal will be going back from the heavy section into the riser. So your riser is sound with maybe some spongy structure. So it is sending the metal, and the metal is coming back. So you may have to increase the riser size, either increase the diameter or increase the height.
In case of 9-inch riser, we can go still 2 inches height more. Right now, that is 16-inch height. So, if 1:2, if we get, then 18-inch height we can get.
Yeah, I think so. I think so. Yes.
But, sir, any additional help will give if you use the exothermic sleeve? If we use exothermic sleeve, can it be helpful in case of insulating sleeve instead of?
No, and that will help in the sense that the exothermic sleeve will keep the riser metal hot, and the metal coming from the heavy section will stop because the metal in the riser is pushing the metal into heavy section. So that will also help. Yes, and that thought crossed my mind before you asked me this question: is can we switch over from insulating sleeve to the exothermic sleeve? So yeah,
Yeah.
you can try that. First, try the higher height insulating sleeve, and then go to the exothermic if the problem persists. What is the distance between your riser and the casting? Sorry, between the riser and the casting at the riser neck. How long is it?
That I have to check. Right now, I don't remember it, but
Okay.
it may be around 75 maximum.
That appears to be almost 3 inches. Yes, that appears to be okay.
Only by grade changing means by switch over
No,
to
see,
higher silicon. Is there any
okay.
effect on
No,
solidification or something?
no. There are two things which has changed over here. One is the grade has changed. The structure has changed. It is fully ferritic structure.
And also properties are okay, sir.
Yeah, properly,
Properties
that's
give
fine.
little.
That means
Uh,
you have read that standard EN 1563 very well. That's why
yeah.
all you said is I am agreeable. Only thing is the shrinkage at the neck.
Yes. Only
That-
problem is that.
That's a little bit of a methoding problem.
No, but literature says that there is no difference in solidification pattern and other things with the grade changing. So
Hmm.
that methoding is not to be. I've read it somewhere. I don't know right now from where I have read it. But literature says that there is no much difference between solidifications pattern in SSS grade and normal ferritic grade. It
I
says
see.
like
Okay.
this with same
Okay.
carbon equivalent.
Yeah. The carbon equivalent is based upon the section thickness.
Hmm.
Carbon and silicon. Because your silicon is 4.2%, which is contributing over to 1.
No, silicon is 3.2%. 3.2
Yeah.
and carbon is 3.1.
Yeah, this is a solid solution to the 3.2 carbon silicon, 3.1 carbon. Uh, just check the modulus of the casting riser combination from the heavy section to the neck to the casting. What is the modulus variation from heavy section to the neck of the riser and to the
Actually,
riser?
by calculation, whatever modulus, right now I don't remember, but modulus, whatever it is coming by calculation of the
Mm.
casting modulus, we have kept
Mhm.
0.7 neck modulus.
Yeah, that is normally the what we keep, but still you're getting shrinkage in the neck.
Yes.
That means uh, you have to increase the metal in the riser.
Neck of the riser is to be increased.
No, metal in the riser. Neck
Metal
appears
in
to
the
be
riser.
okay. Yeah.
But sir, riser having no piping means there is no means, requirement of liquid metal or solidified during solidification. It indicates like that also or something.
Well, I'm looking
There
at it
is
from a
no
different
sign.
way. when
There
the
is no
riser is
sign.
solidifying, it needs liquid metal for feeding, and probably the liquid metal is being pulled from the heavy section, and therefore there is shrinkage in the neck. So before the riser starts solidifying, the riser neck should solidify and choke up any demand for metal from the heavy section. So if you have to choke the riser neck fast, you have to reduce the riser neck modulus.
Okay, we will try by either riser neck reduction, and another suggestion is that exothermic sleeve. If
Keep
we
the
can
same riser neck and increase the sleeve.
height of the sleeve.
Yeah.
There is a question from Mr. Jignesh Somar, how to avoid a ductile iron cast iron fading. So I have replied him that we will send a literature, and we are going to cover the fading topic in a magnesium treatment episode. Meanwhile, we will send technical literature to him. Mr. Vignesh L has asked, sir, nickel promotes the primary austenite during the solidification of SG iron.
Yeah, that's why we have nickel and austenitic SGIN. In austenitic SGIN, we add nickel to make the austenitic structure stable at room temperature.
The next question is by Mr. Sarang Bhalerao. He is asking how to improve elongation in SG iron in 550 by 12 and 500 by 7 grade.
No, you are getting low elongation means the grade, how much is the silicon content? Just tell me the grade and the silicon content. And you want to increase the elongation, as I understand.
We maintain silicon in bath 1.8 to 1.9% and in final 2.6 to 7%.
No, your bath is 1.8 to 1.9% silicon.
1.8 to 1.9.
And final is 2.7.
2.6 to 7. Yeah.
Okay, fine. How much ferrosilicon magnesium we are adding for treatment?
We are adding ferrosilicon magnesium about 12 to 13 kg.
For the batch size?
1100.
Okay, 1100 batch size, about 1%, you can say, 1 to 1.1%, right?
Yes.
So 1.1% silicon will be containing about 0.55 silicon addition.
Silicon addition 1.8.
After that, you will be doing inoculation.
1.12% in 1100 kg.
No, silicon is that the amount of inoculation or amount of ferrosilicon magnesium?
In amount of ferrosilicon magnesium.
Fine. But how much silicon you are getting from 1.1% ferrosilicon magnesium into your metal? About 0.55.
After 1.12% adding, we add adding inoculant, steam inoculant in treatment daddle to 3 to 4 kg excessive.
Section is heavy. Don't consider too much of silicon coming from the steam inoculation. And there is no regular inoculation, only base metal, magnesium treatment, and followed by pouring along with the steam inoculation. This is the process.
Yes, sir.
And you want to increase the amount of elongation.
Elongation, yes, sir.
What is the grade and what is the elongation required, and how much elongation are you getting?
We require 10 to 12, near about 12% elongation in
Yes.
ASTM standard, as per ASTM standard. But we achieve 4 to 5% only.
So you are not getting the required elongation.
Yes.
If you want to increase the elongation, you have to increase the ferrite content.
Ferrite content.
Yeah. Otherwise, where will you get the elongation from? You want to increase the elongation. The elongation comes from ferrite in the matrix, right?
Yes.
And your steam inoculation of 3 to 4 kgs is probably not giving you the required matrix structure. Can you share the copy of your matrix structure along with the mechanical properties results?
Yes, you have ferrite structure of obtaining near about 51 to 50%, and pearlite structure 48 to 48, 47.
Your structure consists of around 10% graphite. So ferrite plus pearlite should be equal to around 90%.
Okay.
Because in your case, the graphite is included in the pearlite content. So reduce the pearlite content by 10% from your figure, and that will give you the pearlite content. So you have to increase the ferrite content to get the elongation.
Then last question is by Mr. DPVS. For cylinder liner in centrifugal casting, what should be the targeted chemistry for grade 600 by 3 for cylinder liners, centrifugal casting?
Centrifugal casting thickness.
Thickness 12 millimeter.
So you want to know the composition to get the 600 by 3 grade in 12 millimeter sections in centrifugal process, right?
Yeah.
In the structure, do you get any carbides on the outside
no.
structure in contact with
No.
the mold?
No carbide.
No carbide. So you have a good coating on the inside of the mold with the centrifugal process. You have a good coating in the mold, on the mold before pouring. That's why you're not getting any carbides.
Yeah.
And you want to know the chemical composition for 12 millimeter centrifugal casting. I had given a chart in the first episode with the different section thicknesses, the composition. I'll refer to it and DP, I'll get back to you tomorrow.
Yes, sir. It is chart is showing for 600 by 4 grade. For 12 mm section thickness, carbon should be 3.7, silicon 2.45, manganese 0.25 max, copper 0.5 max. But if it is a different for centrifugal casting, then you can highlight that.
In centrifugal process, you already have a very fast cooling process. If you reduce the copper, will we not get a higher elongation?
Variation in properties. Hardness variation is there.
No, in centrifugal casting, there will be hardness variation from outside to inside. But how much is the hardness required and how much you are getting?
270 to 300.
And you want?
270 BHN to 300 BHN.
Yeah, this is what is required, right?
Yeah.
And you are getting the hardness of?
Below 270.
Have you considered increasing the copper content?
0.4 copper is adding.
Go to 0.5, 0.55.
Yes, we can go.
Thank you, sir. The last question was from Amarun Foundries, how to avoid the exploded graphite. So I have replied them that we are going to cover that in a casting defects section. But briefly, you can tell some tips, and meanwhile we will send them a technical literature on exploded graphite.
Yeah. On exploded graphite, there are two things. You must have a cap on the carbon equivalent on the higher side. Depending upon the section thickness, the carbon equivalent required to be controlled is decided. So what is the section thickness of your casting?
35 mm.
35 mm. So I think you have to keep the carbon equivalent maximum around 4.35. So what is your carbon equivalent now? You can check it up. Carbon plus one third silicon, forget the phosphorus. What is the carbon content just now? What is the silicon content just now? We can calculate the carbon equivalent immediately.
See, we are getting some one or two nodules getting exploded. We are maintaining the carbon of 3.9 and the silicon of 2.9. 3.5 and silicon 2.9. Carbon equivalent of 3.5.
See, carbon is 3.5 and silicon 2.9. 2.9 divided by 3 is almost equal to 1%. And your carbon is 3.5%. So 3.5 plus 1% is 4.5. And therefore, you should expect to get graphite rotation. 1 or 2, why not? But you should get. You have to reduce the carbon or reduce silicon. But I would say, because the graphite rotation is there, reduce the carbon by about 0.1 to 0.15% in the final.
Okay, so we should, for this casting thickness, we should maintain maximum 4.3 carbon equivalent. Am I right?
Yeah, 4.3, 4.32. Yes, you're right.
Okay.
Friends, those who are there, if you have the queries, you can contact myself or Mr. Hardik on these numbers, or you can send it through email on sales@castwell.com.